right. Well, I guess we can get started. So this week, if you haven't read the announcement or kind of gone ahead, this week we're going to be covering constraints and indexes. And you might wonder, well, what, kind of did they randomly throw those together? They actually kind of go very well together. So we're going to kind of talk a little bit about that. But for the most part, we're going to, because you guys have kind of seen constraints quite a bit, we're going to talk about how they relate to indexes. But I'm not going to go over too much of constraints, but if there's something new that I talk about with a constraint, just stop me and we can go over it. But anyways, I kind of want to just kind of jump into some examples. I've kind of been messing around a little bit. So in the announcement, I kind of gave an example, and I'll kind of walk through it again, but I don't know if any of you here are old enough to remember a time when libraries, like before like computers were really a big thing. Because I feel like I'm not that old. Maybe I'm that old now, but I remember like there's a time when there really wasn't like computers. There was computers, but maybe like they didn't have the software in our local library or something. But I remember like indexes. I remember like if you wanted a book, like they had a filing cabinet or information. And I guess this is still applicable, but everybody had a way of kind of cataloging their books, or libraries did. And in fact, if you're ever bored, there's some really good, interesting reads on catalog systems. Like I think there's one called the Dewey Catalog System, where people kind of had these ideas behind how to organize. Also, like here's the Dewey Decimal System. So there's lots of different catalog systems. Let's see if we can find the wiki for it.
Some of them are really complex, like what goes before what, and yeah.
Yes, and and there was different systems for different purposes. So like basically, like here's our library classification system. Basically, depending on like what your priority was, whether it was speed in finding a category or speed in finding a specific book, or maybe it was the organization itself, because maybe this way is easy to find one book, but this other way is easier to kind of organize the books, like from an employee standpoint. So there was all these different classification systems. And there for a while, before computers, people were very adamant about their version of indexing. We've all heard the term an index card. The reason we have an index card is because they use them to index things. So like they might have had a cabinet, and I don't know if you guys have seen these cabinets, but they're like little square drawers. See if we can find one. Yeah, right here.
I bought one on eBay because I thought they looked cool. They go for like thousands of dollars. They are in demand.
Yeah. So basically all these was a lookup. So, you would go to the index cabinet and, they would have their little system, and you would use the index card to go find your book, or whatever piece of information you're looking for. These concepts apply to all sorts of data. And so anyways, what's interesting is those same algorithms, those same kind of principles apply to computers, but obviously we can just perform them much, much faster. Oh, and like Tim says, the Dewey Decimal System was the bomb when he was in school. Yeah, like that one I know was super popular. But anyways, it's interesting because like, after you see how this works, if you ever get confused, I like to logically go back to how they used to do it, because what's interesting with computers is like it seems more complicated, but really it's the same logic we've been doing for a long time. So anyways, the indexes are going to work very similarly to how we used to do it. So back to our analogy, if we wanted a book, let's say we're looking for a book, and just like, we all do this mentally. If you've ever gone into a Barnes and Noble, I'm a big Brandon Sanderson fan, and I know he signs books occasionally. So whenever I'm in an airport or Barnes and Noble, first thing I do is I go straight for Brandon Sanderson section. And they have their way of organizing it where the first thing you look for, we always start at the broad category and go down because that's the most efficient way, right? So we go and we look for the non or the fiction. I think Barnes and Noble does it by like fantasy. So you look for the fantasy, and then you look for like the S because you see the alphabet kind of laid out. So then you look for the S for Sanderson, and eventually you see his giant books that three of them take up the whole row, and you found them. We're going to do the same thing with our data. And our database system uses that same kind of logic to kind of make it faster. You can imagine someone like Google or Facebook that's sifting through huge amounts of data. Like even when you log into Facebook, think about how many users it has to look up just to make sure your password matches. It's an incredible amount of data, and people are logging in all the time. So obviously we need it to be as efficient as possible. So the way we do that is with indexes. And along with indexes, we can also improve performances with constraints, which we'll talk about as well. So let's say we're going to use our analogy of signing into something. So we have our customer table, and our customer table has an email field. So if I wanted to, let's just see who we have. Let's pick on somebody that's in our email table. I might still be in here. Nope, I deleted myself. Let's pick on someone who's up at the top. We'll pick on Mary Fowler, who's actually Mary Smith. So I'm just going to take and copy this email address. So whenever we log into our system, depending on how it does, we're going to pretend that there's a password field here. Actually, we have system user. Let's check that out. That's something I made. Let's not use that. So we're gonna pretend that customer has all of our information in it. So when we go to check someone's password's valid, we say select, we might select everything from customer where email is equal to that, because we give, as users, we provide the email and the password, and it kind of checks it for us on the server. So let's say we send it our email because that's how it checks, and boom, it pulls all this information. And it did that really fast. And we obviously don't have enough records to really have a good use case to show, but we're going to walk through what it does anyways. So in this case, if we take a look at the customer table, you'll notice that we have a few things going on here. We have a primary key on customer ID, which automatically creates an index. All of our primary keys are indexed. And then you'll notice we have our foreign keys that say key on it. We also have our foreign key here. And let's see if we have any. I don't see any indexes. So let's make sure here. Yeah, I don't see any indexes. So a couple of things we can do to make this faster. So we know our primary key is index, but in this case, people are logging in with their email, meaning it's going to be used a lot. So what we can do is we can actually tell the computer, hey, I'm going to be using this a lot. I want you to index it for me. And if we go back to our old classification system, it's basically like telling the database, this is where the databases are much more powerful. It will automatically essentially create this cabinet for us, really for itself. It creates this cabinet for itself that it uses. So I can say, let's say alter, let's do create index customer email one on customer. See, how does this work in SQL? customer dot, I think it's parentheses. Let's try it like this. Nope. Let's pull up the old documentation and take a look. All right. Oh, I was just wrong by that much. We just need parentheses.
It makes me feel so much better that you occasionally have to look up the documentation.
Yeah, and you'll come to find, so actually I work with three, let's see, Oracle, four. So Oracle, SQL Server, Postgres, and MySQL on a daily basis. And they, even though the concepts are all the same, and really even the SQL's the same, little things like that, like, oh, like, do I use parentheses or a period? Can sometimes like hang you up. So I like to just keep the documentation real handy. So that way it's times like that where it's like, oh, am I doing this right? You can just pull it up. And just, you know, I really like the way the documentation's laid out because it gives you like the basics and all the optional flags as well. So like create index is like anything in these little brackets means you can choose one of those three things. So in this case, we created a index on, and then we gave it our table name and our column. Now we could give multiple keys, which we'll do here in a little bit. But we're going to just start with email. So we just created an index on email. And now theoretically, if we had enough data to actually have it make a difference, we would actually notice a speed increase when we're searching for email. Now, the other thing I'm going to do to make this even faster, this is where the constraints come in. So as we know, email addresses are something that are not usually shared. In fact, they should not be because obviously there's security risk. So let's say we let our people sign up. Imagine if Netflix let other people sign up with your email address. So, you know, I could sign up with Tim's email address, send myself a password reset, and voila, you know, or change my email, whatever, you know, that you can see that there's potential problems. We don't want anyone taking our email, or, you know, oh, I don't ever want Tim to have Netflix, so I hurry and sign up with his email address, and he never gets to use it, or vice versa. You know, there's just problems. So emails are something that we don't want shared. So what we can do is we can make it unique. So I'm going to hurry and drop this index. Actually, let's build the constraint first. So I'm going to alter table customer. Because this should have been done anyways. In fact, that's kind of why I had it up to see if it had already been done. Because you'll notice that our email, the default is null. So it's nullable, which could potentially be a problem, but this table really wasn't built for it. But we're going to pretend that it was built to log in. So we're going to alter the customer table, and we're going to add a constraint. And we're going to say, if I could spell right, customer UK1. And that stands for unique. So what I'm doing is I'm putting a unique constraint on the customer table. And we're going to say the email has to be unique. So now if I were to try to put another Mary Smith in this table, it would say, hey, you can't do that because email addresses have to be unique. So now what we can do is let's drop this index, customer email 1. Drop index. You can leave it. It's fine. We'll drop it later. So now that we have this unique constraint on this customer table, which let's refresh that. Generate our DDL. There we go. So you can see now we have this unique key here. And what this unique key does is it acts like an index for us. which we could create manually by saying create unique index. Just like our documentation showed, we can create a unique index, which basically means that it has to be unique. But what it does is now when it searches through this table, however the magic happens that it does it, as soon as it finds mary.smith@sequilacustomer.org, it can stop looking. Normally, even though, hey, we know we're looking for one person, what if there were two people that had the same email address? It would have to find all the results. But once we put that unique key, that unique constraint, that unique index on this column, once it finds that one row, the database knows, hey, I have a rule built that means that there can only be one of these. So I'm going to stop looking. And so at that point, it stops looking.
Can I ask a question about how that works practically?
Yep.
If you add this constraint after the table's already in existence, is it possible that you already have people with duplicate data? And
Yes.
how that happens?
It won't let you put this on until there is only unique values.
Okay.
Now, that's a great question because, yeah, what if we already had two Mary Smiths? Yeah, if we tried to add a unique constraint, it would actually say, hey, you have to, I can't put this constraint on there because there's duplicates already.
I could be searching and get the wrong one if there's a duplicate.
Yeah. Yeah. So
Oh, this is it.
yeah. So it kind of, it basically, if it has a unique constraint on there, it knows that everything in there is unique. And it actually builds a separate index system for that. And it's hard to go into exact detail on how it goes, all the things that it does. It would probably make my brain hurt. But also I think they're like really tightly guarded secrets for a lot of these. So anyways, that's kind of, I think that's the best example of how a constraint and an index kind of play together to optimize. Because if we have our data constrained to kind of match our business logic, the indexes are often built automatically. So like if we create a unique index, it automatically, or if we automatically create a unique constraint, it will create a unique index. And the reason the database does that is because, like what was brought up, if we already have a duplicate, it wants, every time someone inserts data now, it has to check to make sure there's only one of those. So it actually builds the index so that it can be faster even when you're inserting records to do its own rule checking. So not only does it improve querying, but it also improves inserting data. And surprisingly, I think we learned about this in the beginning of the term. Maybe the book covers it, maybe it doesn't. There's actually engines of MySQL that are better for reading data than there are for writing data, and all sorts of stuff. So the cool thing is that with indexes, they can also help improve write speed as well as read speed. So it's not just about finding data, it can also be improving when you're inserting or updating data as well. Okay, and so another one, another good example I want to go over is a B tree index. So this will be in your reading, but the B tree index, what it does is it will divide the information equally, so to speak. So let's see if we can.
B is balanced, correct? That's why it's called that?
Yes, correct.
Okay.
So let's let me see if we can drop this index now. Customer email on the customer. There we go. I don't know why I was putting the parenthesis there. That was weird. Okay, so if we wanted to create an index, and before I get into B tree, sorry, I'm going to backtrack just a little bit. So we still have our customer data. The other index that I want to create, because let's say we do a lot of searching by first and last name. So like, let's say we have part of our system, let's you search for people based on their first and last name, like our actual storefront, which is probably very, very popular. Like someone comes in the store, says, if you remember the old Video USA type stuff, I grew up in a small town, so it's not like we had cards or, membership cards or anything. So it was just like, oh, what's your name? Search you up and they'd find you. So in that case, we'd probably want to be able to index first name and last name. Now we could create two separate indexes, but that doesn't make a lot of sense because the whole idea behind the index is to uniquely identify rows. So in this case, like, oh, I'm looking for Mary Fowler, not all the Marys. It's probably a very strange case that we would look for everybody named Mary. So we wouldn't want to build an index for that one use case, but we want to look for people, for an individual by their first and last name. So what we're going to do is we're going to build an index that actually uses both columns. So I'm going to say create index customer name 1 on customer. We're going to do first name, last name. So kind of like how we built that first index, but you'll notice this time, instead of just having email here, I have two columns. And if I run this, you'll notice that it worked just fine. And basically what that is now we have an index that is using two columns. And so it actually indexes them kind of together. So now if we were looking for people based on first name, last name, we would be able to find it really fast. So if I was optimizing, if my whole job, and it's surprising, there's actually people whose their whole job is they're consultants, and they just help optimize queries or databases. And so if I were going to do that for these people, I would say, okay, based on you're looking up people constantly with first name, last name basis, I would say let's put an index on first name and last name, but also a lot of your employees, all they do is they just search for last name and then they scroll to find the first name. So they're not really using the first name column all the time. So I would then say, let's create two indexes. Let's create one on the combination and then one just on the last name. But you'll notice that it says duplicate index defined. This is deprecated and will be disallowed in a future release. So one point that I wanted to come across here is that if we're using a duplicate entry here, we don't need to worry about doing it individually, because the way this works is it kind of indexes both of them and does its magic to kind of put them together. So if you're using a multi-column index, you don't need to worry about doing the other ones, and which is really handy because you can imagine that a lot of people might say, well, why don't we just index everything? And that's also a bad idea, because then you actually don't get any, it's actually degradation in performance, because every time you index something, just like we said, it creates that filing cabinet. It actually creates more data. So indexing is one of those things that you want to do for the things that matter, and that's it. Use sparingly.
Should
Okay.
I add that indexes take up a lot of storage space? The more index you have, the more storage space you consume.
Yep, correct. Yep. Every time you create an index, like I said, I kind of used it as a metaphor, but it's also very real. It creates that little index cabinet. And every time we do that, we're using disk space, which is all obviously very handy. So yes, not only are you going to see degradation in speed, but you're also going to see degradation in storage, which you want to balance that all the time. Like that's obviously like a big concern. All right, so now let's cover that B tree. So now that we have our index on our first and last name, um, we're fast, but we kind of want to go back to our email thing. So I'm actually going to let's create index. So this was our kind of original index that we kind of did. But one thing we're going to do is we are going to, let me actually, so I don't get any issues here. Prop constraint. I don't know if I need all to the table for that. There we go. So let's drop that constraint that we made so we don't get any issues here. So this was kind of our original index where we said, oh, let's index the email. But we talked about our B tree index and someone brought up like, oh, that stands for balanced. And so that's kind of, that's kind of the way I like to think about it is if we have, in fact, let's just pull a list of our customer emails. So if we were going to pull this and let's order it alphabetically because we are, it's a var chart data type. So we obviously know that it has alpha characters in it. So we're going to sort it alphabetically, alphanumerically. And we can see that in this table, we have 599 rows. So basically, if we were going to do let's just leave the database out of this for a little bit. If we kind of wanted to develop our own system to kind of help find things faster, let's say we had an index card for each one of these email addresses, and we were going to put it in our index cabinet. So we've got we've got a few drawers. Let's say we're just dealing with a traditional filing cabinet. We have 4 drawers. And we want to say, okay, let's develop a system that's the fastest way to identify these rows. So we might say, oh, well, let's put A through E in drawer 1, and then D through whatever in the next one, so on and so forth. Let's divide them up. But let's say we do that, we might have one drawer that's, full, like we can't fit any more in. And so our method isn't going to work for very much longer because what if we add another A and we're already full? But our Z cabinet is like empty. So basically, instead we decide, hey, let's take our 600 records and let's divide them up equally. So we're going to take, if we have 4 cabinets, we have 600 records, we're going to take 150 records, roughly, and put them into each cabinet. And then we're going to label the first email address and the last email address on each cabinet. So that way we know, hey, if I'm looking for a Hank, I can go immediately to where the H's would be and go from there. The database is going to do something very similar with a B tree. So let's say using B tree. So basically, when we use the B tree, it's going to divide up all of our records equally by row number. So what we see there on the left-hand side. And it kind of creates an index. So it knows kind of where things are at. And so if I'm looking for Mary Smith, it knows, hey, I can skip rows 1 through, let's just make a guess. I can skip rows 1 through 460, right? So it can say, I'm just going to start here. So then it can start here and then it can say, okay, now I'm looking for the S's and then it only has to read in 1,000 rows instead of 3 million or whatever. Or in our case, instead of loading 600 rows, it knows, oh, the SM Smith would be in this quadrant. And so then instead of loading 600 records, it loads 20. So on
And this is where you said the unique comes in because then once it finds it, it doesn't keep going through the rest of them.
Correct. Yep.
Okay.
And the way it organizes this, it might still know like, okay, all of our S's, like Smith, exists in this quadrant. So, because I know that 539 is Terra, 516 is HSA. So I know that if there's any Smiths, because I sorted it, it exists in this, or I guess I'm looking at the wrong thing here. But if there is any, it would exist within this kind of quadrant. And so I only have to check all the records in this quadrant. So even if we didn't have a unique index, it would still be pretty good in knowing like, oh, I'm in this quadrant. That's what I need to look for. But if we have that unique index and that makes sense with our business logic, yeah, we'll speed it up, because let's say that there's someone like Facebook, their database still might have, 1 million records in a quadrant, or however it decides to do it. As soon as it finds that record, it knows it's done, because we know that there only is one Facebook account that has my username, because that's how it looks me up. And so, it makes sense to put that on there. So that way, once it finds it, stop looking. We don't need to waste resources going through the records that we know are not going to match our query. So if we create this index, it's going to do just that. It's going to put it in the quadrants, and away it goes. And just to kind of show, there's this really cool tool called explain. And let's run this query here. All right. So what's cool about this this tool explain is it tells you kind of what the database is doing. So we can see like the select type is simple, the table is customer, partitions, it's null, reference, but then it'll say possible keys. And then it says the key it uses to search it, and it tells you the key length. And it can even, I think this even tells you the cost. There's like SQL Server. I know I've never really done it with MySQL, but I know that SQL Server, for example, like I could run this explain command, and it would tell me like, oh, like how much resource cost is this query? Because then I could say, oh, it would actually let me see what step takes the longest. And can I mitigate that? Can I put an index on it? Is there something I can do to make this better because it takes a long time to run, or I just need it to run every 5 minutes, something along those lines. So this explain command is really cool because it shows you that it uses that key. Now, just for kicks and giggles, I'm going to drop this index.
Can I ask a question about something that's in the book and that I can see, but I can't get to work on my SQL?
Sure.
When you do this explain, it shows instead of using the semicolon, you can do a \uppercase G, and it's supposed to put it vertical instead of horizontal, so you can see everything. But it's not working on mine, and I don't know if it's a setting or what.
That is a good question.
Because I know I can click on, like in the
Workbench.
Yes, there's a little button on the side that says form, and it puts it that way, but you're supposed to be able to use this \G to put it vertical, like it's supposed to be telling the server to do that, but I couldn't get it to work.
Let's see. Let's pull up our handy dandy manual here. Reference manual explain statement. Explain. There is a format name. Format equals tree. Let's see if we can
It's right there. You can see it on line 1 at the bottom of your screen, where he has the \, or
I see. Yep. Okay, let's Let's try it. That might be the analyze, but we'll give it a shot here.
And it's supposed to be
Oh.
in lieu of the semicolon. And it has to be in uppercase, I believe. It's a different thing.
Gotcha. Let's try it here. There we go.
Okay,
Cool.
I'm going to try that and see if I can. I kept trying and it kept giving me an error to check my version or something.
Gotcha. All right. So one thing that I wanted to show here. So we dropped our index. So this is without the index. And what's cool is we can see this cost 61.25. I saw when we were looking up that other command. So thank you, because it was helpful for more way than one. So we can see our cost is 61.25, and we can see our time and all that kind of stuff. So what I'm going to do is I'm going to re-put this index on here, because the other thing I wanted to shows up here. This is, I guess, spoiler alert, but this is with the index, and this is without the index. And you'll notice that the seconds are the same, but what I want to point out is this filtered. So basically what this filtered means is that it could skip 100 records essentially when we use the index. So that was 100 records that it didn't have to read and check, versus without the index, it was not as good. It could only filter 10. So we're going to put this to the test. We're going to create this index back on customer email tree. Ooh, and look at this. This is interesting. So our cost was 61.25 without the index. Our cost with the index is 0.35. So you can see that's pretty significant. Pretty significant as far as costs. I mean, and we can barely tell a difference, right? Like our time is, well, our time was actually about half, even though it was a blink of an eye for us, really. Took no time at all. But the bigger you get, the more you're going to want to kind of pay attention to this kind of stuff, because it can make a big difference. And I've actually gotten kind of, when I first started doing this, I was kind of I didn't understand it as well, I guess you could say. And so I would kind of just start building tables. And I didn't really think about this kind of stuff, because I thought, oh, I can optimize later. Like I just want to make it work. But the more and more I've gone along, the more I've realized, like, oh, this is a lot easier to do while you're building it, because it doesn't take a lot. You just got to think like, okay, like, yeah, I'm going to kind of like what you guys have done with your UI maps, right? Like kind of map it all out. And then once you kind of have that, you say like, oh, I'm logging in with the email. So I'm obviously going to be querying single records on the email. So this is something that you might want to put a unique index on. Or, oh, I let people look up recipes by the name of the recipe. So maybe I want to put a B tree index on the recipe name, stuff like that. Because, there's someone who's making a project with U2 albums. So maybe the album name, maybe you want to put a B tree index on the album name, so on and so forth, just so that way it's improving. Not that you have to for the project, because this, honestly, we're in week 12, which is crazy, and we're getting more into like the end game type stuff. So don't go and change your project for it, but it is something to be aware of. And if you want to play with it on your final project, feel free to do so. You can put it in your final paper or in your paper and stuff like that. But anyways, I've rambled on for 45 minutes. Does anyone have any questions about indexes and constraints? Okay. I actually really like indexes and constraints because to me they make sense. Like with the because they're logical. If you ever get stuck, like, oh, should I put an index on this or not? Like imagine that all your records, the rows in your table are in a filing cabinet and you have to try to find them. What would you do to organize your filing cabinet? And then once you kind of go through that mental process, then you can say, okay, this is how I would organize my filing cabinet. So like, for example, if we're checking people's passwords manually on paper, we would want to organize by, whatever they're using to kind of get in. So their email address. And so obviously if we want to look up by that, we want to put an index on it. The beautiful thing is versus the old days, we can index by multiple things without having 12 cabinets sitting around that people choose, choose if you want to look up the book by its ISBN number, or choose if you want to look up the book by the author last name, so on and so forth, or choose if you want to look up the book by the reading level. There's lots of different things that you might do, but anyways, it's kind of fun. All right, well, I don't want to take up too much of your evening. Does anyone else have any other questions or comments before we sign off here?
I don't know if it needs to be recorded, but somebody put something in Teams last week and they answered the question on the, I want to say, I don't know if it was the quiz. I think it was the quiz. They answered it the same both ways, but it was wrong one time and it was correct the other time. I don't know if you had a chance to look at it. Nobody else posted. I think it was Sister Ashley Whitening had posted.
Yes.
And others have said it's happened.
Yeah, so
but
there's been a couple, and what's hard is like it's pretty much same question but different answers. So basically what's going to happen on those quizzes is everyone will basically get points for those.
Okay. But the question is what database only row locking is according to the textbook? And then it said many answers possible. But in the book, only Oracle is only row locking, but other databases can do row locking. Is that correct?
Yes, and it's kind of, that one's kind of a question I don't like, because in a lot of cases, it just depends. Oracle is the only one that kind of does exclusive row locking by default.
Right.
Other systems can do it, but maybe not by default, and some do it for certain things and not others. Oracle is the only one that kind of does it by default. So I think the question is just kind of it's kind of loaded, if you will. So I don't like that question. The answer is the short answer is no. Like a lot of them can do row locking, row level locking.
Mm-hmm. Okay, thank you.
Yep, great question. All right, well, I don't want to keep you guys any longer. So if something comes up, feel free to shoot me a message or an email. I'm more than happy to help out. Just as I guess, last little bit of housekeeping, we are down to the wire, like on final projects. So if you're close, you might just want to think about just getting those wrapped up. Feel free to shoot them in, and I can get them graded. Because like I've said in the past, like if something is missing, which I don't really foresee there being any problems, but if something is missing, if you turn it in early, you'll have time to maybe fix something, or like, oh, I forgot to include this one document, or oh, I just forgot to do that document. You can hurry and do it, because like if something's missing, I'll more than happy to let you adjust it so you can get your points. So if you're doing a final project, just a reminder that that's coming up awfully fast. It's scary how fast the time goes. But anyways,
Project turned in like this week. Do we continue to write papers of just about the basic prompt instead of about our final project? Is that kind of how you would?
yep. Or if you want, you're more than welcome. Like if maybe like, oh, what would I have done had I, like, for example, like if I would have known about a B tree index, what would I have put it on in my project, sort of thing.
Oh, perfect. Okay.
All right. Well, thank you guys for being here. If anything comes up, just feel free to let me know. Yep. Have a great week.